Hi, so in this last part of the tutorial, I'm going to be showing you how to do image classification. Um, yeah, this is a really popular and successful application of machine learning. And so the idea is that the input in these kind of problems is going to be an image file, which is represented as an array of real numbers with, one dimension corresponding to the number of the height in pixels of the image, another dimension corresponding to the width in pixels of the image, and another dimension corresponding to the number of channels. So, for example, in an RGB image, red, green, and blue channels, that means there's 3 channels. But in this tutorial, we're only going to be using images with h number of height and number of width both equal to 16 pixels and only 1 channel. So that's corresponding to grayscale images. So smaller values in this real valued array mean darker parts of the image. So when we're talking about classification, that means the output that we want from our learn function is this class or category y from a finite set. So that's in contrast to the previous tutorial where we were looking at regression problems where the output was a real number prediction. So here we don't want to predict a real number, we want to predict what class the image corresponds to. So we're going to be considering images of digits, and so there's 10 different digits, and so there's 10 different possible classes each image could be. So we're going to represent that as y could be in any of the digits from 0 to 9, right? So what we want, if we want to learn a function f, such that f of a 0-digit image is going to give us the 0 integer, and f of the 1-digit image is going to give 1 integer, etc. for all the other digits, right? So here's an example of 12 different observations from this image digit data set that I'm going to show you in a little bit. And so the idea is that each one of these panels shows you one observation. And we see the label of each one of these images in the panel title, right? So here, this is the image of the number 6. And if we see the label, the corresponding label is indeed a 6, right? So here we can see some variation, right? Both of these are have the 6 label. Both of these have the 1 label, so we can see some variation between the two. So here, these are both 0 labels, right? And yeah, again, to give you an idea of what we're looking at, I mean, every observation is actually just, again, a matrix, 16 by 16 matrix, where each one of these entries in the matrix is got an intensity value between -1 and 1, right? So the -1s correspond to the dark black areas, the 1s correspond to the bright white areas, and then the gray values are somewhere in between. So what we want to do in every case is we want to take all of these intensity values as input and then output the corresponding label value. That's what we want our algorithm to do, or what our learned function to do. So the representation of these digits in a CSV file looks something like this. So every one of the different images is one row. So here's the rows that correspond to the same images that we see in the previous slide. The first row here is, sorry, the first column, so here's a typo. It says the first row is the output label class to predict, but actually this is the first column here. First column is the output label class predict. So here we want to, this is a did image of a 6, this is the image of a 5, this is the image of a 4, etc., right? And so the other 256 columns here are pixel intensity values. So what it means is that these 256 values and these other columns over here can be combined to make that 6 image that we see here, right? So same thing for every one of these other observations. So often, I mean, most of the time in machine learning, you'll see that the data set is in this kind of CSV format. So it's important to kind of get used to handling like these CSV data tables as inputs to your machine learning algorithms. And so yeah, again, the idea is that we want to take all of these 256 pixel intensity values as our input, and we want to be able to use those values to predict what the corresponding output label is. And so to plug that into a neural network, what we need to do first is for these multi-class classification problems, we need to do like a one-hot encoding. This is what we call it. And the idea is that, well, so we want to be able to create this matrix where, again, the different rows correspond to different observations of different images, and the columns correspond to the different classes. So here, from 0 to 9 again. The idea is that for any given image, so remember the first one was labeled 6. We're going to have all zeros except for a 1 in the 6th position, right? So same thing for all of the other ones. So there's always going to be a 1 in just one place in every row. And so to do that, to construct that kind of one-hot encoding, which we need for plugging into the machine learning algorithm, we need to first read the data table into R. And so here I'm doing that using this data table : fread call. So again, what that means is use the fread function in the data table package. And that's again reading a CSV data table into R. And the idea is that here we're going to have some file on disk called zip.gz. This is a gzipped data table of these data points that we see like this. And you can see my code on the GitHub repository if you want to see the details about how to download that data file and everything. But the idea is we save that in this zip.dt, this data table representation of the CSV file. And then what we can do is we can call this Keras : two categorical function on that first column. So ziptt $v1, that means the first column of that data table that we read. And so that we're going to be storing that in this zip ymat object, which is going to look something like this. So these two functions handle that conversion for us, basically. So after that, to plug into the neural network, we need our inputs as an array in R. So we can use this function array to create that. And so what we need to do, first we define the size of the images. So it's 16 by 16 pixel images again. And so when we use our array call, what we can do is that we can specify the first argument data as, here we're using unlist ziptt. So this means we're treating the data table as just, unlist means not treating it as a data table anymore, but just as a standard atomic vector of numbers. And so that's necessary for use with this array function here. And so what we do is we select all of the rows, and just and this -1 here means we're selecting everything except for the first column. So again, the first column was the label, so we want to ignore that when we're constructing this input X array. And so then we have to specify the dimension of this array. And so again, it's going to be the number of observations, which is the number of rows of that data table as the first dimension. It's going to be this zip size of 16 for the second and third dimensions, as the height and the width of the image in pixels. And finally, the last dimension 1, that's going to be the number of channels, right? So it's only one channel because it's a grayscale image. And yeah, so that's all we have to do for constructing the inputs and the outputs for plugging into this machine learning library. We're going to be using this Keras library, which really simplifies definition of and learning of different neural network models. And the idea is that, to define a simple linear model in Keras, all we have to do is we start with this Keras model sequential call. We put it through this pipe operator to kind of chain the different layers together. So this percent greater than percent thing, this is what we call a pipe operator in R. And so what it means is to kind of combine these operations together. So in the end, it's going to end up with this linear model variable here, which is going to be assigned the value of, starting with this Keras model sequential thing, adding on a flattened layer, and then adding on a dense layer. So you have these different layer underscore object functions, which can create different layers in this Keras framework. And these different layers correspond to, different kind of modeling choices that you have when you're designing your neural network, and they're all going to lead to different generalization ability, so different prediction accuracies. So I don't really have time in this tutorial to go through all the details here, but suffice it to say that in this case, we're using the layer flatten call to convert this array, which is an input shade of 16 by 16 pixels in one channel, to, we're converting that kind of array to kind of a flat vector of 256 numbers. And then after that, we're plugging into this layer dense object which has 10 units here, because that's the same as the number of possible classes for an output, right? There's 10 different digits, so we have 10 units in this final output layer. And this activation equals softmax is required for the last or output layer in all of multi-class classification problems. And again, that's just something that ensures that all of the predicted probabilities of each class sum to 1. So that's how you define a simple linear model using this Keras neural network modeling package. And after you define the model, what you can do is you can use the compile function to specify a loss function, which is, this is the thing that's directly optimized or minimized in each iteration of the gradient descent learning algorithm. The optimizer here, this is which version of the gradient descent learning algorithm to use. And the metrics here, this is an evaluation metric that you might want to monitor in addition to the loss. So it's not directly optimized via gradient descent, but it is, there are various metrics which are typically more relevant or interpretable for the application. So here, accuracy means the proportion of correctly predicted labels, which is a very interpretable and relevant metric for classification problems. And so, if you want to know what different kinds of losses and optimizers and metrics are available, you can go to the Keras API webpage, and it describes all of the different options you have for putting in these 3 categories here. And the final step that you need to do in order to learn your Keras model is called this fit function, where you call as a first argument, first and second argument have to be this X array and this Y mat object that we created in the previous slides. And the idea is that these are going to be the trained data that we're going to be using to learn how to get good predictions using the given model. Second argument here, or third argument here, epochs equals 50. Well, this is the number of full passes of gradient descent through the subtrained data. And so another way to think about that is in each epoch of gradient descent, we're computing the gradient with respect to each subtrained observation exactly once. So after we've gone through a whole epoch, we've seen each subtrained observation once. And finally, we can specify validation underscore split equals 0.2, and that means to use 80% of these data observations here as subtrain and 20% as validation. So again, the subtrain set is for gradient descent parameter updates, and the validation set is for hyperparameter selection, like controlling overfitting. And so when we do that and we learn the linear model with Keras, we see these kind of characteristic learning curves that we saw in the last tutorial, where the subtrain loss is always going down as a function of the number of epochs or the gradient descent passes through the subtrain data. And then with respect to the validation set, well, we see it goes down up to a certain point, and then it starts to kind of flatten out and even go up a little bit. Right, so it says that for this model, I mean, probably we shouldn't go more than about 40 epochs through these data. So another model that we can define using this Keras framework is a convolutional neural network, and these are really successful in image processing applications. So as we'll see, we'll get a much better accuracy with this convolutional model, because it's really exploiting the structure of image data to make learning easier and faster. And the way it does it, was with this layer conv 2D. This is a 2D convolution layer. And the idea is that you have to specify a certain number of filters, which is basically kind of the number of hidden units in this layer. And the idea is you also have to specify a kernel size, which is kind of like the number of pixels in terms of height and width that these filters will be applied to the input image on. But the idea is that we're going to be kind of learning different filters for kind of sliding along in different patches of the image to kind of see different patterns in the image. And so it's going to be able to detect maybe different edges of the different digits or different kind of things using these convolutional layer. And so yeah, here we specify activation equals ReLU, that's rectified linear units, and the idea is that here you have to specify some kind of nonlinear activation function for the to get better results than the linear model. So to see what the different choices you have for the activation function, again, you can look at the Keras API documentation. The next thing that we haven't seen yet is this max pooling 2D layer. And so sometimes these are useful in combination with the convolutional layers in order to get kind of models with fewer parameters and also better generalization ability. So again, I'm not going to go into the details about these max pooling layers, but you can look at the API docs to look a little bit more about what are your choices there with the different parameters here. Finally, yeah, in this we call layer flatten to get a vector of hidden units, and then we have layer dense to get 100 hidden units in this penultimate layer. And finally, in the final layer, we're going to have units equals the number of columns or the number of outputs that we're trying to predict again. With the softmax activation. So this is kind of like the last layer, which is always required in the multi-class classification problems. But so when we do that, we kind of see some learning curves which look more or less similar, right, from what we've always been seeing. The subtrain error is mostly always going down as a function of the number of epochs, whereas the validation error goes down up to a certain point, and then it starts to kind of flatten out and maybe go up a little bit. But you can see the absolute values are quite different here. So here, the validation loss gets down to about 0.1, whereas in the previous slide it only got down to about 0.2. So maybe that's a big difference. Anyway, so let's look at a third neural network model. So this is a dense or fully connected neural network. And so to do this, well, we start out with a layer flatten like we did with the linear model. And then we follow that with a bunch of layer dense objects. And so here I'm doing it 8 times just to get a model which has about the same number of parameters as the previous convolutional neural network that we were looking at. And then we're finally finishing it off with the same layer dense, which is just defined by the number of output classes that we have. So if we fit that model, we get something that looks like this, where the subtrain loss going down up to a certain point and starts to kind of oscillate. So, because of the way that the neural network is designed, it's not always guaranteed to decrease the subtrain loss in each epoch of gradient descent. So sometimes you do see this fluctuation, and when you do, you might consider changing the optimization algorithm. Like I said, there's different choices, but here I'm not going to worry about that. Anyway, we see that going down more or less, and then we see the validation loss going down, and then more or less flattening out as well. So after that, if we plot all of those subtrain validation loss curves in the same plot, we see something that looks like this, where we can see that convolutional validation loss is quite a bit lower than the other two, right? These are the blue curves here. And that kind of suggests that maybe the convolutional network might do a better job for held out test data prediction. So to really answer that question, we have to do another kind of split though. So we'll use fourfold cross validation for model evaluation. And so what that means is that we want to answer this question: does the convolutional model provide more accurate predictions on unseen test data? So to answer that, we have to first randomly assign a fold ID to each image or observation. Then for each one of those test fold IDs from 1 to 4, what we do is we hold out the images with the test fold ID as a test set. So those, say we're doing test fold ID 1, we're holding out all of the images which were randomly assigned test fold ID 1 as a test set. So they're not used at all for model training, not even in this picture here where we're using the validation set. So the test set is something totally separate that we set aside at the very beginning. And so then we use all of the other images to train the other 3 models using validation split equals 0.2. So these other images, this is going to be called the train set, and the train set is going to be split further into subtrain and validation set using this validation split argument to the fit function. After that, we're going to plot the validation loss curve as a function of the number of epochs and select the number of epochs which minimizes the validation loss. And so that's what we were seeing in the previous figures. And again, so that's totally ignoring this first test set that we held out at the very beginning, right? It's not used at all in this calculation of the validation loss curves. And so yeah, this step is essential. It's the hyperparameter learning step. So at that point, we figure out what is the good number of epochs, right? So here, given this validation loss curve, we can say that about 10 epochs is the right number of epochs for this particular neural network and this particular data set. And so after having learned that, what we do is we actually retrain with epochs equals that learned number of epochs. So in that previous case, we'd say retrain with epochs equals 10, and then with validation split equals 0. So that means use all the training data for gradient descent parameter updates. So still, we haven't used any of the test data yet. So the final step is that we compute the prediction accuracy of this retrained model with respect to the held out test set. And so that's where the test set finally comes in at the very end. We finally have the learned model, and all we're using the test set for is just make a prediction on those test set and see what the prediction accuracy is. And then what we do is finally we plot the accuracy value or the mean of SD over folds after testing 4 times. So 1 for each test fold, because we're doing 4-fold cross validation. So if we do that, what does it look like? The accuracy rates for each test fold in this case look something like this. So the idea is that here it's always a good idea to compare the your learned models with the trivial baseline model. And that's what I'm showing here in this last row here in the plot. And so this baseline model is always predicting the most frequent class in the trained set. So it ignores all of the inputs and features, and it's always just looking at the training data and saying, okay, hey, the 0 digit is the most frequent. Let's just predict all of the test images are 0 all the time. Of course, that's going to fail quite a lot. And so actually the accuracy rate is below 25% in this case for the baseline model. And so we can see that, we can use that as information to see that all three of learned neural network models, the linear, the dense, and the convolutional model that we saw earlier, all three are clearly learning something which is non-trivial, so much better than the baseline model. And so it's always a good idea to run that baseline just as a reality check to make sure your models are learning something at all. And so if we zoom into those three models which are learning something, what we see is that this dense network with 8 layers is learning something a little bit better than the linear model that we saw in the beginning of this tutorial. But the convolutional model is doing quite a lot better than both of them, and between 99 and 100% accuracy with respect to held out test data, right? So that's really good. And so the conclusion is that in this particular data set, the convolutional neural network should be preferred over these other two. But one thing to keep in mind is that this is really data dependent. Machine learning is an empirical science, so this conclusion about this particular convolutional neural network and this these particular other models, this really only holds for this one data set where we've done this test. So we always need to do a cross-validation experiment to see which model is best in any given data sets, right? So in a different data set, maybe we have the dense model which is working better. I don't know. You have to do the test to find out. And then the other thing to keep in mind is that, maybe in this particular data set, other models and algorithms would be even more accurate. So these are only 3 possibilities that I had time to explain, but, you can imagine adding, another option over here, a few more options on the y-axis here. You could, ideally you run like 10 or 20 different algorithms and you just take whichever one works the best, right? So, you have options of, if you're using this Keras package that we were talking about, you can play with the number of layers, add more or less layers in your neural network, add more or less hidden units per layer, or you could try to, ditch Keras and use a completely different algorithm for machine learning. I didn't have time to talk about, these other popular machine learning algorithms, which are completely different from neural networks, but they are also highly effective, and you should definitely try them if you're concerned with getting a good prediction accuracy. Like, for example, random forest boosting. There's lots of different examples, and so so the take-home message is that what we did is we in this tutorial we learned how to define and learn neural network models, and then also finally make figures like this which show the test accuracy. So this is accuracy with respect to the held out test set in the fourfold cross validation. So we can conclude that for this particular data set, the convolutional network is working the best, and we would want to use that if we have more unseen data that we want to make predictions on that look similar to these data. But, again, these conclusions really only hold for this particular data set. Maybe even in other digit data sets, we would have different models which are working better. So we always need to do cross-validation experiments like this to see which model is best. And, again, you probably want to try more than just a few models. A good rule of thumb is at least 5, 10 or 20 is a good number of machine learning models to try if you're really concerned of getting good prediction accuracy. Okay, well, thanks for listening, and I hope you enjoyed my tutorial.